Hello, am I audible?
Yes, sir.
Okay. So I think you go through with the week two content. Anyone go through with the week two content?
Yes, sir.
We start the week two. Yes, shall we start week two?
Sure, sir.
Sir, I had one. Maybe we can take it at the end. One question in the practice assignment for week one that uses Taylor series approximation.
Okay. Okay, we will take in the last.
Sure, sir. Sure.
So have you gone through with the week two content?
Yes, sir. We can go ahead. Yeah.
Okay. Yes, anyone is saying something? Any girl?
No, sir. I was saying okay only.
Okay. So basically in week two, they start with the number system. Okay. So we have a three different types of basically four different types of number systems are available. One is the binary, second is decimal, third one is the octal, and last one is the hexadecimal. Then we have a sign magnitude number. One's complement, and two's complement. Okay, so these are the number systems. So mainly the four types of number systems. And these are the representation of negative numbers. Representation of negative numbers. Okay. Now binary number system that will be represented as a base 2. That will be represented as a base 2. The only possible combination is the combination of zeros and ones. Only two values will be defined, 0 and 1, and the combination of zeros and 1. That will be defined, that is called the binary number. In the decimal, the base n is possible and the values will be from 0 to 9. In the case of octal, base 8 is possible and the values is from 0 to 7. And hexadecimal, the base 16 is done and the values is from 0 to 9. Then 10 represent as a, 11 as a B, 12 as a C, 13 as a D, 14 as a E, and 15 as a F. Okay, so these are the 15 from 0 to 15 will be represented. Okay, now the thing is that where we use this one. Okay, so for our understanding, what we do, we are basically when a number is given like 8, 8. So what we are thinking, this is the 88. Okay, so generally the base is 8, 10. Okay, so it is a easy understandable for use for a user. We can easily understandable 88, but we can't understand what is the meaning of B7, what is the A3. So these are not understandable. We think that A is the alphabet and 3 is the number. So it is a alphanumeric number. But basically this is the number. Okay, so the decimal number is easily understandable for us. Now, the initial level microprocessor or microcontrollers, or we can say the laptops, your mobile phones. So in initial level microprocessor and microcontrollers, they can understand only the binary number. Binary number. Because initially microprocessor and microcontroller that are available is 1 bit. Microprocessor and microcontroller. So they can understand either 0 or 1. Because these microprocessor and microcontrollers are somehow digital devices. So they can understand 0 and 1. But the problem with the 1 bit is that only two levels is defined, either 0 or 1. Either 0 or 1. Like for example, if I say I connect a microprocessor or microcontroller, I just connect a microprocessor with a sensor. Temperature sensor. Okay. Microprocessor or microcontroller. Now, this temperature sense the temperature, environmental temperature, and it will be send the value either in the form of 0 or 1. Now, the temperature lies from 0 to 45 degrees centigrade. So, which will it consider as a 0? So, like for example, we consider that 4 degree or 5 degree will be considered as a 0, and above 40 degree will be considered as a 1. Okay, less than 4 degree and greater than 40 degree will be considered as a 1. But what about in between these two? So we can't identify the temperature that lies between 4 and 40 degrees centigrade. So this is the problem with the 1 bit. So we go with the 8 bit microprocessor and microcontroller. Microprocessor or microcontroller. So in 8-bit microprocessor and microcontroller, initially we go with the octal number representation. Nowadays we are using the representation in the case of hexadecimal. Hexadecimal. Okay. The best example is your laptop Mac. Laptop Mac ID. If you go with the laptop Mac ID, that is a 16 or hexadecimal representation. The MAC ID is like A8 column B6 colon C T colon B9, like this way. Okay, so it is a hexadecimal representation. Clear? So these are nowadays these are used. If you go with the next term, the digital system design, where we are using the hexadecimal representation. Okay, so these are the uses of this binary number system, this number system. Now, in the case of binary, like for example 101011, this is the binary number. The thing is that how we convert this binary number into the decimal number. So basically, if we convert any other number except decimal to decimal number, the best way is basically we use this one for the binary number. If we convert any binary number into the decimal number, we multiply with the weighted. Okay, weighted summation. What is the meaning of weighted summation? Is that 101011. Now, this particularly is called the LSB. LSB is least significant bit, and this one is called the MSB, most significant bit. So we multiply with the weight. Multiply with weight. Okay, and weighted summation. So we add this. Add this. Okay, and we introduce the weight. So initially LSB will be the weight as 0, 2 raised to power 0. Then 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, and 2 raised to power 5. Okay, so this multiplication is the weight. Okay, this is the weight. Every bit has the weight. This is the weight. This one is the weight. Okay, so these are the weights. So weighted summation. Okay, now if we add these two, so 2 raised to power 5, 32 multiplied by 1, that is 32. 2 raised to power 4 multiplied by 0 is 0. 2 raised to power 3 multiplied by 1 is 8. 2 raised to 2 multiplied with 0 is 0. 2 raised to power 1 multiplied by 1 is 2, and 2 raised to power 0, 1 multiplied by 1 is 1. So it is a 43 of base 10. Okay.
Yes, sir.
So this is the this is the basically conversion from binary to the decimal. Any number, like for example 11010, or we can say the extended number. So 111 0 1 0 1 and 1. Now multiply with 2. summation and now weight 0, 1, 2, 3, 4, 5, 6, 7. So 1 plus 2 plus 4 plus 8 is 0 plus 16 plus 0 plus 64 plus 128. 250. Okay. So in this way, we convert the any binary number into the decimal number. So this is the basically conversion from binary to the decimal. Binary to now in a similar way we can convert decimal to the binary. Not in a similar way. Decimal to so like for example 56 base 10. If we want to convert into the binary, so it in this key process we multiply the weighted and after that we summation. Here what we do, we divide 56. So we divide into three segments. Okay. In the last one, we just put as a reminder. Okay. So 2, 56, 28, reminder is 0. Again divide by 2, 14, reminder is 0. Again 2, 7, reminder is 0. Again 2, 3, reminder is 1. Again 2, 1 and reminder is 1. Now we can write in this form from MSB to LSB. This is your MSB part and this is your LSB part. So the answer is 111000. Base 2. Okay, like in a way we can solve as a 127 base 10 into the conversion. We can put as a 129. 129. So 129 to 64, 128, 1 is a to 32, 0, to 16, 0, to 8, 0, to 4, 0, to 2, 0. Again 2, 1, 0. So from MSP to LSP. The answer is 10000000. Okay. Any doubt?
No, sir.
Now, if we are talking about the maximum representation, so 1-bit binary can represent maximum 2 values, either 0 or 1. Okay. Similarly, 2-bit binary can represent 0, 0, 0, 1, 1, 0, and 1, 1. So maximum 4 values. 3-bit binary can maximum represent from 0, 0, 0 to 1, 1, 1. Total 8 values. Okay. So we can represent as a 2 raised to power n, where n is number of bits. Okay. 2 raised to power n values will be represented. Okay. And maximum value will be lies from 0 to 2 raised to power n minus range. Okay, for example, n is equal to 1. So how many values will be represented? 2 raised to power 1, that is 2. And what is the range? 0 and 1. 0 and 2 raised to power 1 minus 1, that is 0 to 1. If n is equal to 2, so 2 raised to power 2, that is 4 values will be represented. And the range zero to 2 raised to power 2 minus 1. That means 0 to 3. Any doubt in this part?
No, sir.
Okay. Now, the octal number. Octal to binary. In the case of octal, the maximum range is 8. 8 values will be represented from the range 0 to 7 to binary. So what is the basically matter is that if any octal number is represented, like 567. Okay. So if I want to convert into the binary, what should I do? I should represent every particularly digit into their respective binary number. Into their respective binary number. So 7. If I want to represent 7, so 2 raised to power, so 3, 1 carry, 2, 1 and 1 carry, so the value is 1, 1, 1. So 7 should be represented as a 1, 1, 1. 6, 2 raised to 3, 0, 2, 1, 1. So 1, 1, 0. So I should represent the 1, 1, 0. And 5, 2, 1, 2, 1, 0. So 1, 0, 1. 1, 0, 1. So this is the binary representation of a octal number. Okay. So octal to binary representation is easy. Four 36. So we should represent every number 4, 3, and 6. Okay, so first of all, we have to understand that if 0, I can represent 0 as a 0, 0, 0. 1, 0, 0, 1. 2, 0, 1, 0. Okay, basically the weight of this one is 1, weight of this one is 2, and weight of this one is 4. So if we required a 2, so the weight of 2 should be 1. If we required a 3, so weight of 2 and weight of 1 will be added. So 0, 1, and
Sorry, I can't help with that.
okay. Now 4, so weight of 4 should be 1. 5, weight of 4 plus weight of 1. So 4 plus 1. 6, weight of 4 and weight of 2. And 7, weight of 4, 2, and 1. Okay. So now 4 should be represented as a 1, 0, 0. 3 should be represented as a 0, 1, 1. And 6 should be represented as a 1. So this is the octal to binary. Okay. Any doubt? Yes, any doubt?
No, sir.
Okay. Now the thing is binary to octal. So in the case of binary to octal, what we do? We make a group of 3. But remember that starting with LSB. Starting with LSB. Why starting with LSB? I will explain you. Okay, starting with LSB. Okay, now represent the octal value with respect to each group. With respect to each group. So if any binary number is represent 1, 1, 0, 1, 0, 1, 1. So I have to represent with the in the octal. So what should I do? I just make a group from the LSB. This one, and 1 is alone, so I can use 2 zeros. I can use 2 0. So what is the value? This group value is 0, 1, 1. So weight of 1 and weight of 2, 3. The second group value is 1,
5.
0, 1, 5. And last one is 1.
1.
Okay. Now, if we are going to start a group from the MSB, so what is the values? 1, 1, 0, 1, 0, 1. So one group is this one group is this one, and we have to add 2 zeros here. Now, what is the value?
But sir, that will be wrong, right? Because
Yeah,
that
I will tell
difference the
you. I
value.
will tell you what is the wrong in that. Why it is wrong. Okay. So the answer is 4,
5.
5, and 6.
Yes, sir.
But that is wrong. Why it is wrong? Because when you add zeros in LSB, the decimal value is changed. Decimal value is changed. Whereas when you add zeros in MSB, no change in decimal value. No change in decimal value. I just take one example. 1, 1, 1. Okay. What is the answer of this one? What is the decimal value of this one?
15.
7.
Yes, sir. 7, sir.
Okay. If I add a two zeros in the LSB part, so 1, 1, 1, 0, 0. Now, what is the decimal value of this one? Wait, 1, 2, 4, 8, 16. 16 plus 8, 24 plus 4, 28. Base 10. And if I add these two zeros in the MSB part, 0, 0, 1, 1,
It will
1,
stay the same. 7.
that is again a 7. So if we add a zeros in the MSB, no change in the decimal value. But if we add a zeros in the LSB, so decimal value is changed. Clear? Now go to this part. If we start a looping from the LSB part and MSB group is not created, so what we do? We add two zeros. We add two zeros. So adding these two zeros doesn't create any effect on the values. Whereas when we start the grouping from the MSB part, okay, and LSB side, if there is no group is created, so we added 20 and that particularly changed the values, complete value. So that's why this way is wrong. This way is wrong. Clear? So that's why we start a grouping from the LSB part. So always remember that start a grouping from LSB, not from MSB. Is it clear?
Yes, sir.
Yes.
Now binary to hexadecimal or hexadecimal to binary. Initially hexadecimal to binary. Now in the hexadecimal, the maximum value should be represented between 0 to 15. Okay, 0 to 15. And we saw that with the 3-bit only the maximum value is 7 is possible. So for the representation of 15, we required a more number of bits. So now the weight is 8, 4, 2, 1. So 7 we already represent. If we go with the 8, so the value is 1, 0, 0, 0. The value of 9 is 1, 0, 0, 1. 8 and 1 addition. 10, 8 and 2 addition. So 1, 0, 1, 0. 11, 8, 2 and 1 addition. rest is remaining 0. 12, 8 and 4 addition and rest is 0. 13, 8, 4 and 1 addition. 14, 8, 4 and 2 addition. And 15, 8, 4, 2 and 1 addition. Okay. So any hexadecimal number. B8C hexadecimal. We already discussed that in the hexadecimal 9 till 9 it should be similar to the decimal, but 10 should be defined as a 11 as a B, 12 as a C, 13 as a D, 14 as a E, and 15 as a. Okay. Now B8C. So what is B? B is 11. So I can represent every particularly hexadecimal bit with respective their 4 binary digits. So B is 1011. 8 is 1000. And C is 110. This is binary. Okay. Now similarly way A1C 16. A is 10, 10, 10. Now 1. Don't be
0,
confused
0,
that
1.
1 should be 001, but it is a 3 digit. We have to
Yes, sir.
represent every digit in a 4 bit. Okay. So that's why it is a 0001. We have to add 10 in the MSB from the conversion from 3 bit to the 4 bit. So 0001. And C is 110. Okay, so every particularly digit should be represented in a 4 bit. Don't be confused that till 7 we can represent in a 3 bit. Okay, till 7, like for example 735 in a hexadecimal number. So 7 should be 0111, not in 3 bit, in a 4 bit. 3 0011 and 5 0101. So in every case we add 10 in the MSB part. So that is the binary. Now binary to hexadecimal is similar. First of all, make a group of 4 bit. And represent with respective hexadecimal value. Again, remember that when you are going to create a group of 4 bit, start with LSB. Start with LSB. One one 1 0 1 0 1 1 0 0. So we create a group of 4. One is this one. One is this one. 1 is this one, and 1 bit is remaining, so I can add a 0. Now 1000. So 1, 2, 4, 8. So it is a 8, 1, 0, 1, 0, 0, 1, 0, 1. So it is a 5, and 0, 1, 1, that is 7. Okay. Now decimal to octal. The way same as similar to a decimal to binary. What we have to do, we have to divide with 8. Okay, so 389 decimal into the octal. So 389 divided by 8. So that is equal to 605. Okay, decimal to octal. There is another way also if you are getting confused with that. So first of all, you convert decimal to binary, then convert binary to octal. Okay, so the answer should be same. So if we convert decimal to binary, so 389 divided by 2, so 1 is remaining, 194 divided by 2, 97, 0 divided by 2, 48, 1 divided by 2, 24, 0 divided by 2, 12, 0 divided by 2, 6, 0 divided by 2, 3, 0 divided by 2, 1 and 1. This is the answer. So 11000 0 101. Now we create a group. So group is this one, group is this one, and group is this one. So it is a 6, 0, and okay. So the answer should be same. Now, octal to decimal. That is also similar to the binary to decimal. We are taking the same number 608, 605 base 8 is equivalent to base 10. So we do the weighted. So 5 into 8 raised to power 0 plus 0 into 8 raised to power 1 plus 6 into 8 raised to power. So it becomes 5 plus 0 plus 64 is a 380. 384 plus 5, 389. Okay. Again, there are different way. Then you can convert octal to binary. Then binary to decimal. Okay, this is also a one way. Okay. Then decimal to hexadecimal. Way same. 389 base 10 into the hexadecimal base 16. So what should I do? Again, I divide with 16. Sixteen. Sixteen on the 16, 8. So 185. The other way is decimal to binary and binary to hexadecimal. So the way one. Way two is decimal to binary and binary to hexadecimal. The number is 101000011. Okay, now so binary number is this one. Now we convert into the hexadecimal. So this is the 1, 2, and third one we are adding 3 zeros. So it is a 5, 8, and last one. So 185. Okay. Now hexadecimal to decimal, again same method. Hexadecimal to decimal. Same method, like for example 185 base 16. We have to convert into the decimal. So we multiply with the weighted 185, 16 raised to power 0, 16 raised to power 1, and 16 raised to power 2. So that is 256. plus 16 8 ja 128 plus 5. So that is 389 base. Okay. And second way is convert hexadecimal into binary, then binary into decimal. Okay. And last conversion is from hexadecimal to or octal to hexadecimal. So the way is that initially we convert either hexadecimal or either the octal. We first convert into the binary, then hexadecimal, and binary, then octal. Okay. A31 into the octal. So A is 1010, 30011, and 1 is 0001. Now create a group of 3. 1, 2, 3, and 4. So it is a 5, 0, 6, 1 base. Okay. And similarly, octal to hexadecimal 3, 6, 7, 3 into base 16. So we represent into the binary. So 0, 1, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. 3 is 0, 1, 1. Now make a group of 4. 1, 2, and 3. So it is a 7, 8 to 10 and 11. 11 is B. 8 to 10 and 11. It is again B. So 7 BB basis. So this is a all representation. If you have any doubt related to this one, you can ask. Any doubt with this conversion part?
No, sir.
Okay. So today we cover all the conversion. Now in the next class we represent the negative number. Sign magnitude 1's complement and 2's complement. Okay.
Okay, sir. Sir, can we take up that practice assignment week 1 question?
Yeah. Yes. Which question? Practice assignment. Question number.
So 15, the last one. Yeah, Taylor series approximation using Taylor series.
Given that VA is 10 volt, okay, determine the operating voltage V in so that an incremental gain of 10 is achieved. Okay. So what we have to do is we are using the Taylor series expansion. So what is the formula for Taylor's expansion is? E raised to power x should be represented as a 1 plus x square upon factorial 2 plus x cube upon factorial 3. Okay. Here it is mentioned round to the 4 decimal place. Okay. Now
Okay, sir.
here it is given e raised to power in the place of x, it is given as a v in upon va. V in upon va. So it is a 1 plus v in upon va plus v in upon va whole square plus v in upon va whole cube. Yeah, divide by 6 and divide by 2. And that particularly is also multiply with va. Okay, and that is equal to v out. Now can we cancel the va? So 1 plus v in plus v in square divided by 2 times va plus v in cube divided by 6 times va square is equal to v out. Now put the value of va.
V is 10 volts.
And given that the incremental gain of the 10 is achieved. So what is the meaning of incremental gain?
So dv0 by dvi v in is defined as the gain, right?
Yeah. So incremental gain is dv out upon dv in. And that is 10.
Okay.
Okay. Now can you solve it?
Okay, so we differentiate it and
Yeah, we differentiate, put the value of va, and after differentiation we can put that 10. So here it is a square will be a normal 1
right.
v. So this is the 1, this is the 2v in, this is the 3v in square, and here it is equal to the 10.
Okay.
Okay, and now we put the value of va and calculate it.
Okay, sir. Okay.
Yeah.
Okay. Thank you so much.
So only one parameter v in is remaining. Now.
Right.
Okay, after differentiation, one parameter v in is remaining. Va is given, dv out upon dv in is given. So only v in is the only parameter. We can solve the value for v.
Okay, sir. Okay. Thank you.
Any other doubts? Okay, so thank you all.
Thank you, sir.
Thank you, sir.